So far we have seen the evolution of the telescopic op-amp from the regular one stage op-amp. So the really important things to note are that you replace the differential pair with a cascode pair of transistors, and you replace the upper current mirror by a cascode current mirror. So in other words, you create a cascode section for both the upper section and the lower section. Now let us look at a very qualitative, at a very high level, let us look at what would happen in the circuit when driven with differential signals, and later we will move on to the small signal analysis. So let us assume that I am applying voltage of plus Vd by 2 and minus Vd by 2 to the inputs of the op-amp. Now, as always, I am going to assume that this common source node of M1 and M2 of the input pair is a small signal ground. This is of course valid because the devices on both sides are highly identical, and the current through the transistors M1 and M2 is symmetrical. So therefore, the bias current of course splits equally between the two paths. So all bias currents in the except for M0 are I0. So the bias current through each transistor in the circuit M1 to M8 is I0. Of course, the current through M0 is 2I0. Now, since the common source node of M1 and M2 is a small signal ground, the current through M1 is Gm times Vd by 2 downwards. The current through M2 is of course Gm times Vd by 2 upwards, where Gm is Gm1 and which is also equal to Gm2. Now what happens to this current? So let us look at the current through the left half. So if I look at this current has two paths to flow. One is through the resistance of M1 itself. So if I were to look at the current flowing Gm times Vd by 2, I am looking only at transistor M1. So this current can flow through two paths. The first path is through RDS1 itself. The second path is upwards into transistor M3. For that I need to find out the impedance looking upwards through the drain of into the source of M3. This impedance happens to be very close to 1 over Gm3. So most of this current flows through transistor M3. Therefore, we can say that this current is Gm1 Vd by 2, and so is this current. Now what happens to the current through the left side? The current flowing through the left side flows through M7 and M5. So both those currents are also Gm1 Vd by 2 flowing downwards. Now this will generate a small signal voltage Vx at this node, and that will cause a small signal current to flow through M8, and again that current flows through M6 and finally flows through the into the output node. Now at the output node, the current flows out. Now this current, since this circuit has no load, the current will flow through the overall output resistance at the output node. As you can see, the two currents flowing from M6 and M4 are in phase and will add at the output. So I out is ID6 plus ID4. This is nothing but Gm1 times Vt. So the output voltage that is generated is I out times R out, and R out is nothing but the impedance looking upwards and downwards. So let us see what R out is. R out is R up. So the impedance looking upwards and in parallel with the impedance looking downwards. So let us write that down in red color. Is R up parallel R down and R up is equal to GM6 RDS6 times RDS8 and R down is GM4 RDS4 times RDS2. So you have two cascode resistances. One cascode resistance looking upwards, which is the output resistance of the current mirror, M5, M6, M7, M8, and you have the resistance looking downwards, which is the cascode resistance of M2 and M4. And therefore, the overall voltage gain is extremely large. So VO by VD is the overall voltage gain of the circuit. This is nothing but GM1 times GM4 RDS4 times RDS2 in parallel with GM6 RDS6 times RDS8. So this is the voltage gain of the circuit. This is clearly of the order of GM RDS the whole square, because you have the product of two GMs and the product of two RDSs. So now we have got the gain from an DC gain from an op amp that is of the order of the square of the intrinsic gain of a single amplifier. Now this is clearly much larger than the original one-stage op amp. Now let us quickly point out a couple of things. Now if you look at the overall GM of this device, so if you look at this op amp is also best represented by an operational transconductance amplifier, because it has a transconductance and a very large output resistance. This is the output resistance and the transconductance is nothing but GM1. So as you can see, the transconductance of the telescopic OTA is the same as the transconductance of the original one-stage op amp. Is the same as the original one-stage op amp. So that is something very important. The other thing to note is that if you were to drive some load capacitor CL, you will now have a pole at the output node. As we saw in the case of the one-stage op amp, the output node was the dominant node, and same is expected to be the case here. So the output node contributes the dominant pole. Now let us, now that we have drawn the block diagram, let us now look at some of the details of this circuit. So now let us quickly find out the output resistance of the portion looking upwards. So we want to find out what will happen if you were to apply a current I test going into this particular current mirror, because we want to find out what Vx is generated at this node. So if I were to excite this current mirror with I test, I want to find out what the input impedance of this particular structure is. So let us draw the small signal equivalent circuit of the left hand side portion alone. As you can see, the right hand side portion will not come into the picture for small signal analysis for finding out the input resistance. So let us draw the small signal picture of the left hand side alone. And let us mark the node. So this is drain 5, this is drain 7. I can now remove this portion of the circuit with nothing in the circuit being affected. So let us do that. So I'm going to call this node D5, this node D7. So clearly D5 is the node which is being excited with my test current source. This is D7. And the gate of M7, which I'll call G7, is also shorted to this particular node. And of course, the gate of M5 was originally connected to some bias voltage VB5, which we will now connect to ground. The source of M7 is connected to small signal ground, and the source of M5 is the same as the drain at M7. So let us now excite this with a test current source I test and figure out what Vx is. Vx is the same as V test, and that will tell us what the Vx by It will tell us what the input impedance of the circuit is. So let us now write down the relevant equations for this particular circuit. So now let us call this voltage Vy. So Vx and Vy need to be determined. So now of course this current is Gm7 times Vx, and this current is Gm5 times minus Vy. So now if you were to apply KCL at node D7, you will find that the total current flowing up is again It, because the same current It splits into these two paths and combines to flow out into Vy. So It is equal to Gm Vy over RDS7, and we will now write this as Gm7Vx plus GDS7 Vy. So this is our first equation, and from this we can say that Vy is It minus Gm7Vx over GDS7. Next we will write KCL at D5. Again we can say that It is equal to Vx minus Vy over RDS5 plus minus GM5 V1. So this is nothing, so we will now rewrite this. So I test is GDS5 Vx minus GM5 plus GDS5 into Vy. Now Vy itself is IT minus GM7 Vx by GDS7. Therefore, we can say that GDS7 IT is equal to GDS5 Vx plus GDS5 into GDS7 into Vx plus GM5 plus GDS5 into GM7 into Vx. I am combining this term times this term to give me the second Vx term. Finally, the third term is minus GM5 plus GDS5 times IT. Therefore, IT times GM5 plus GDS5 plus GDS7 is equal to Vx times GM5, GM7, GDS5 plus GDS5, GDS7. Now, we will now say that all GMs are much larger than all GDSs. So in other words, we are saying that all the transconductances are much larger than all the output conductances. So if you apply this approximation, IT times GM5 is approximately equal to Vx times GM5 times GM7, and this tells me that Vx over IT is approximately equal to 1 over GM7. So please note that the impedance looking upwards R out or Rin is 1 over GM7. Please note that this means that this indicates that there is inherent feedback by connecting the drain of M5 to the gate of M7. So this is very similar to taking a common or taking a transistor and connecting its own gate to its source, its drain. The Rin for that is 1 over GM. Now it turns out that even for a cascade current mirror, this feedback action gives you an input impedance of 1 over GM7. So this simplifies the equation a lot for us, because the small signal model can now be simplified in a large manner. So we will now draw the small signal equivalent circuit for the overall system. So now the impedance looking upwards is simply 1 over Gm, but I also create a voltage Vx, which is this current, let's call that I times 1 over G. So remember that this Vx is now connected to the, note that this Vx is now connected to the gate of M8, and therefore the current through M8 would be correspondingly Gm times this voltage Vx. Gm8 times Vx. This is RDS8. So now let us complete the rest of the small signal picture while keeping this in mind. Now for the bottom portion of the circuit, we are now going to replace the cascode devices, also signal equivalents. The small signal equivalent of the cascodes would be a transconductor of value Gm1 times Vd by 2 and a resistance looking out downwards, which is RDS1, which is RDS of 1 times Gm RDS of 3, and that is the output resistance of the cascode. So RDS1 into Gm3 RDS3. Similarly, on this side, the circuit becomes this. This is minus GmVd by 2 minus Gm1Vd by 2, and this resistance is again the same, which is RDS1 into Gm3 RDS3. As you can see, now the signal current direction is as follows. This current Gm1Vd by 2 has two paths to split. The input resistance looking upwards is much smaller than the input resistance looking downwards. In other words, 1 over Gm7 is much smaller than RDS1 into Gm3 RDS3. Therefore, if this current were I1, all of this current I1 flows upwards into M7 and M5, and that generates a voltage. So now we can now write the right subscripts here. The voltage Vx is equal to 1 over Gm7 times I1, and this is nothing but and of course the current directions are downwards, so let us use the correct current directions so that we don't make a mistake in the signs. So this current and this current is being pulled by I1, so I1 flows through 1 over Gm7. This is approximately 0 because it is such a large output resistance. Now Vx is now minus 1 over Gm7 into I1. So clearly, so I is equal to minus I1. So Vx is minus Gm1 by Gm7 times Vd by 2. Now the current through M2 is simply Gm1 Vd by 2 flowing upwards. Now Vx also generates a current through M8, so let us call that I8. Now I8 is nothing but GM8 times Vx. So this is nothing but minus GM1 GM8 by GM7 times Vd by 2. Since GM8 is the same as GM7, this is minus GM1 Vd by 2. And remember that I8 flows upwards, which means there is a current GM1 Vd by 2 flowing downwards into this node. So the current flowing downwards is minus I8, which is GM1 Vd by 2. So now you have current of M2 which is flowing upwards, which is GM1 Vd by 2, and current of M8 which is also flowing downwards into the same node. So the total output current is nothing but the total output current, let's call that I out, is minus I out from M8 and M2 into the output node is equal to GM1 times Vd. Now what resistance do they flow through? Please note that this resistance of course is not RDS8. This is RDS8 into, this is the cascode resistance looking upwards, which is RDS6 GM6 RDS6 times RDS8. So this resistance is actually because we have drawn the simpler equivalent circuit of the upper cascode transistors. Now this current I out flows into the output resistance of the overall op amp, which is GM6 RDS6 times R, looking in parallel with GM3 RDS3 times RDS1, or GM4 RDS4 times RDS2 looking downwards. So this output resistance of course gets multiplied by I out to give you V out by Vd to be equal to GM1 times R out. So this is the gain of the op amp, clearly is of the order of the square of the intrinsic gain of one single device.